So we started with the design of reinforced concrete columns, wherein first we looked at the types of forces that you can expect in a reinforced concrete column. Then what do we call a column and what do we call a pedestal and what do we call and what is called as a beam column. Then we classified columns on three criteria. The first one was based on the type of reinforcement. It can be classified as tight column or spiral column or composite column. Then based on the type of loading, we classified it as axially loaded column, then column with axial load and uniaxial bending, and column with axial load and biaxial bending. And we also looked at typical examples of these types of columns. And finally, the most important classification from a structural design point of view was based on slenderness ratio. That is, we classified columns are short or long. This classification was based on something called a slenderness ratio. So if the slenderness effects were significant, we said that the column is long or slender, and if the slenderness effects are insignificant, then the column is short. Short columns typically fail uh, with material reaching its ultimate strength, whereas long columns fail uh, at relatively low compressive loads by buckling or elastic instability. Then we sort of revised a term that we learned in the last semester, that is effective length. We looked at how the boundary conditions affect the effective length and how effective length in turn affects the strength of a column. Then we looked at the difference between the theoretical value of the effective length ratio and the value that is given by the code. And we also looked at the reason why these values are different from each other, and the values in the code are slightly greater than the value that we get theoretically. Finally, we were looking at the actual design, that is actual code requirements for designing the columns. The first thing that we looked at are slenderness limits, wherein we looked at an established concept that the slender the column, the lesser is the load that it can take. And therefore, there has to be a certain upper limit to this. You cannot have as much slender a column as you want. So we saw that the upper limit to this is a slenderness ratio of 60. So in no case will your slenderness ratio be greater than 60. We looked at an example wherein we said that if it's a 6 meters unsupported length, so the minimum dimension in that case that your column should have is 100 mm. So this is where we stopped. And I think we also looked at minimum eccentricities. So when when we say that a column is under pure axial compression, it means that there's going to be no or minimum amount of moments. But even though we can theoretically say that a column is going to be under axial load, but practically there it will be under moments because of a number of factors. For example, say a building or a structure is designed only for gravity loads. It is not designed for lateral loads like earthquakes, winds at all. But if some of these loads in different magnitudes act on the structure at the time, there's going to be no resistance to these. And therefore, the structure of the columns have to be designed for a minimum value at least. I think we also gave an example of live load placements, wherein we looked at the example of your classrooms. And even though both of the classrooms have the same span, they have the same functional requirement, they are going to be designed for the same magnitude of load. But just imagine that one of the classrooms is filled and the others is empty. In that case, you're going to have differential loading, because of which you'll have a larger moment in one direction and a smaller in the other, and which can cause eccentricity and thus moments. Then there are a number of reasons like accidental loads, errors in construction itself, and so on. So every column, what the code says is that every column has to be designed for a minimum moment, even though you're sure that it is going to be subject to actual compression, but still it has to be designed for a minimum moment or a minimum eccentricity. Now I've been using these terms parallelly as to minimum moment and minimum eccentricity. So what is the relation between moment and eccentricity? So just to explain with the help of a quick sketch. So if I say this is a column and it is going to be subject to pure axial compression, means that the axial load is going to be concentric. or as someone said, the actual load is going to be passing through the centroidal axis or the longitudinal axis of the column. Now, when I say that the column has to be designed for a minimum eccentricity, what it means that we a certain amount of eccentricity has to be considered in the design. Okay, before jumping to that, let us just understand what is the relation between minimum eccentricity and minimum. So when the load is acting at a certain eccentricity, suppose the load is P and the eccentricity here is E. I can rewrite this load, or I can relook at this load in this way. So I can say that the load is acting at the longitudinal axis. The load is P, but also there's an additional moment of P times E because of this eccentricity. So I have converted a load that is acting at a certain eccentricity to a load that is acting through the centroid of the column, through the longitudinal axis of the column, along with a moment that is equal to P times E. Therefore, when I'm designing the column for a minimum eccentricity, it means that I'm designing the column for a minimum moment. And that is what the code says. So you design it for whatever value of actual load that comes from the analysis, but also design it for a minimum value of eccentricity or a minimum value of moment. Now let us look at what this value is. The code says that every column has to be designed for a minimum eccentricity of L by 500 plus D by 30, where L is the unsupported length of the column and D is the dimension in which dimension in the direction in which you're looking at. So if we assume that, say, our L is 4 meters, so L is 4000 mm, and let us say the dimension that we have given is 300 mm. So we have a 300 mm column. So in that case, if we look at the equation of the code, the minimum eccentricity would be L by 500, meaning 4000 divided by 500 plus D by 30, which is 300 by 30. So this turns out to be plus 300 divided by 30. So this turns out to be 18 mm. Please pardon my 8. So this turns out to be 18 mm. But the code also gives another criteria where it says that it should at least be 20 mm. So we compare 18 with 20. So this should be greater of 18 or 20 mm. So 20 mm governs. So the code says that it has to be designed for a minimum eccentricity of 20 mm. Now, what does this mean? What it means is, if from your analysis, you get that the actual load that is going to be acting on the column is, say, 1000 kilonewton. Then the minimum eccentricity, and if the minimum eccentricity is 20 mm, therefore the minimum moment for which you will design it is 1000. It is kilonewton times 20 mm, which is 0.02 meters. So this is equal to 20 kilonewton meter. So you will design the column for an actual load of 1000 kilonewton and a minimum moment of 20 kilonewton meter. So this is what minimum eccentricity criteria means. Any questions here? Okay. Is it too difficult to understand?
No,
It's cool, right? Okay. So
yeah.
that is what minimum eccentricity means. Simple. The next parameter is regarding reinforcement and detailing. As the code gives a certain criteria for minimum reinforcement that we should put in the columns, maximum reinforcement that we should put in the columns, then the minimum number of bars that we should put in the columns. To start with, let us look at minimum reinforcement. The code says that the minimum reinforcement has to be at least 0.8% of the gross area. Now the question is why? We already know that concrete is good in compression. So we could just right away have a concrete column without reinforcement. So the question is why is it that the code says that there has to be a certain amount of minimum reinforcement? The answer lies in what we just studied, that even though you're sure that it might be under pure axial compression, but there are a number of reasons practically because of which there could be lateral loads, because of which there could be moments. And hence, your column should have a minimum flexural resistance or a minimum bending resistance. For this, there has to be a certain minimum reinforcement. Another reason is to prevent the yielding of bars due to creep and shrinkage. Have you heard of these terms before? Creep and shrinkage.
No.
Okay, so to understand creep, let us take a simple example of your hardboard writing pad. Uh, I'm sure all of you must have used it. You notice that over a certain period of time, it sort of takes it starts taking a deflected shape, and and after some time, it deflects so much that it is not usable anymore. So this deflection is because of continuous load that we have been putting on it. We've been using it for years, and and because of that sustained load, it sort of starts attaining a permanent deflection, and after a certain point of time, it is not usable anymore. Similarly, if concrete is under sustained load for a long period of time, it sort of starts deflecting. It sort of starts deflecting. It develops strains, and these strains, if they're not taken up by someone else, the concrete is going to crack. To avoid this, we provide a certain minimum reinforcement so that uh, firstly, the strain from concrete is transferred to steel, and the amount of steel is sufficient that the bars do not yield. So, two reasons. First is that there has to be a normal flexural resistance, and second is to make sure that the strain due to creep and shrinkage are transferred from concrete to steel, and there is sufficient amount of steel to take these additional strains and the resultant additional stresses. Okay. Then the code also says that the maximum reinforcement that you can provide in a column is 6% of gross area. So now we have got a range that is 0.8% to 0.6%. Even though the code says that 0.6%, but practically we target the maximum reinforcement that we target in actual practice is only 4%, because even 4% is a lot of reinforcement. So we sort of adhere to this criteria that is 4%, that's it. We don't go beyond it. Now, a simple reason for this is that there has to be space for concrete to go through. Now, the column junctions are already very heavily reinforced, meaning that there is reinforcement from beam in one direction, beam in other direction, and also from the column. So there's already a lot of reinforcement there. So if there's no if there's no upper limit to it, it is going to be very difficult for the placement and compaction of concrete. So for that reason, the code says 6%, but practically we follow 4%. Then the code says that the minimum diameter of the bar that is to be used is 12 mm. 8 and 10 are available, but for columns, the minimum is 12 mm. If the column is rectangular, the minimum number of bars is 4, one at each corner. If it's circular, the minimum number is 6. All these bars should be equally spaced. Then the maximum spacing along the periphery should be 300 mm, meaning that if your column is 300 by 300, you can provide 2 bars at each base. So 4 bars is enough. But if your column is say 300 by 600, I think it's uh, better if I draw this. So if your column is 300 by 600, and if you just stick with the criteria of providing minimum 4 bars, what will happen is here the spacing would be less than 300, but here the spacing would be somewhere around 500 mm. I'm just giving an approximate number. Okay, don't take these numbers for real. So this is greater than 300, which is not acceptable, and therefore what you'll have to do is you'll have to provide 6 bars at least. So in this case, practically what we do is say if you require 4 bars of 20 mm diameter, but in terms of detailing, this is not acceptable because this is greater than 300. So what we do is we switch to 6 bars of 16 mm diameter. Okay, just let me make sure that the example that I've given holds good. So this is 6 times 201 is 126. Okay. So what we would do is, assuming that 18 mm diameter bars are available, what we would do is we provide 6 bars of 18 mm diameter. The point being, if the number of bars of a higher diameter are okay from a design point of view but not detailing point of view, what you could do is you could always reduce the number of bars such that you satisfy both the criteria, that is strength and detailing. And the last criteria is about transverse reinforcement. So a quick question: why is transverse reinforcement or stirrups provided in beams?
To resist the shear, I guess.
Yes, simple. To resist shear and torsion. Similarly, now if you look at columns, uh, they are going to be subjected to compression and they may be subjected to flexion. Providing concrete and longitudinal reinforcement should suffice. So, but in all the columns that we've seen, there's always transverse reinforcement. The reason for providing this reinforcement are there are multiple reasons for providing this reinforcement in columns. The first one is to prevent premature buckling of individual bars. So, um, just a moment. So if I draw a column in elevation, say this is concrete and then this is reinforcement. Okay, so if when compressive force is applied, it is going to be distributed in reinforcement and in concrete. So if I look at individual bars, so this is a bar that is being subjected to compressive force. Now, though there's concrete in and around it, but there's a high possibility that this bar might buckle if it is not restrained. Meaning that if there are no lateral ties, the bar might buckle. And therefore, to prevent such a premature buckling of individual bars, we need lateral ties or spirals. Now, another function that these ties do is that they confine the concrete in this region. So when compressive force is applied, the, so you can look at it as, if I just draw this in plan, this is our column, this is our longitudinal reinforcement, and this is our transverse reinforcement. So what this transverse reinforcement does is that it confines the concrete in this region. And it has been experimentally found out that confining not only improves the strength of concrete but also the ductility of concrete. So this is an important function that the transverse reinforcement performs. Then a practical reason is to hold the longitudinal bars in position during construction. Now, if you have happened to visit a construction site, you must have seen that bars coming out of the of under construction columns, and there are always ties around. So these ties hold the longitudinal bars in position during construction. And finally, if required, the transverse reinforcement resists shear and torsion. Now, just like we have criteria for minimum number of reinforcement, then minimum area, maximum area for longitudinal reinforcement, there are also certain criteria for transverse reinforcement. So there are two criteria. One is diameter and other is spacing. The code says that the minimum diameter that you can use is either 6 mm or the diameter of the longitudinal reinforcement divided by 4. Okay, so the minimum diameter has to be greater than equal to 6 mm or diameter of the longitudinal reinforcement divided by 4. What this means is if you are using for longitudinal reinforcement, if you are using 20 mm diameter, so for the stirrups, the diameter has to be greater than equal to 6 or 20 by 4. 20 by 4 is 5. So 6 governs because it has to be greater than equal to or greater of these. Now, if you are using say 32 mm diameter, so your stirrup diameter, so diameter of the transverse reinforcement has to be greater than equal to 6 mm or 32 by 4, which is 8 mm. So what you'll provide is 8 mm. Therefore, the diameter of the tie has to be greater than equal to 6 mm or phi long max divided by 4. Now, what does this phi long max means? So, if you are providing say 4 bars of 32 and if you're providing the inner bars of 20, it means that you cannot consider 20 for your criteria, you have to consider 32. So for this, you will go here. You will consider 32 as your diameter of longitudinal reinforcement, and with this criteria, you have to provide at least 8 mm diameter bars. Now, this might look like a lot of information, but as we solve problems, you'll realize that this is very simple. And the next one is spacing of ties. So the code says that the maximum spacing of the ties should be the least of these three, that is the least lateral dimension of the column, 16 times of diameter of the longitudinal reinforcement, or 300 mm. So what this means is uh, so if you have a column that is say 400 by 300, that is provided with 6 bars of 20 mm diameter. In that case, as per our first criteria, the diameter of the stirrup has to be greater than equal to 6 mm or 20 by 4. We have already seen that this is 5, so we'll provide minimum diameter as 6. Now the spacing of transverse reinforcement has to be less than equal to least lateral dimension, meaning that minimum of 300 and 400, which is 300, then 16 times of diameter of the longitudinal bar, which is 16 times of 20, which is 320 mm, or 300 mm is an absolute limit. So if you look at these three numbers, the minimum value is 300. And therefore, what you'll provide is 300 mm. So the transverse reinforcement that you'll provide is, say, T6 at 300 center to center. That's simple. You just have to remember these criteria for the diameter and spacing. There's no other calculation for this. In case of beams, we have to first find out how much is the amount of shear, how much is the amount of torsion, is the torsion considered in the design? If yes, then we have to find out the final shear force. Based on that shear force, we have to find out the diameter of the ties and the spacing of the ties. But in columns, we do not expect a significant amount of shear and torsion. Therefore, satisfying these criteria suffice the design purpose. Any questions here? Okay, so we jump to the final part, which is the actual design of actually loaded short columns. So in the design of beams, I hope you remember that we had a certain failure criteria. We said that if the maximum compressive strain reaches the value of 0.0035, the beam has achieved its ultimate limit state of flexion, or the beam has failed. Similarly, we have a maximum strain criteria for columns under axial compression. If the column attains a strain of 0.002, we say that the column has reached its ultimate state of collapse in compression. So for beams, the value is 0.0035. For columns under axial compression, only the value is 0.002. Now, we have looked at the stress strain curve for concrete. So this value is 0.002 and this value is 0.0035. Does someone recall this value? So this is stress here, this is strain here. What is this value here?
0.87.
0.87 is in case of steel. This is 0.87 Fy. So for concrete, this value is 0.447, which we approximate at 0.45 FCK. Come on, we have solved so many problems from beams. We have now for every beam, for almost every beam, we have drawn this stress strain variation. We have derived this everywhere. This value that we have considered is 0.45 FCK. I think there's really lack of revision from your side in terms of what we are learning in the lectures. And I just hope it improves over time. And this does not get reflected in your internal marks. So this value is 0.45 FCK. For a strain value of 0.002, this value is 0.45 FCK. So this corresponding stress in concrete is 0.45 FCK. Now, similarly, the corresponding stress in steel, it depends upon which grade of steel it is. If it is 250, now perhaps we'll have to go back to the stress strain curve of steel. We already have mild steel here. Yes. So for mild steel, even at 0.002, this value reaches 0.87 Fy. But we have seen that for if it is a high strength steel, we draw this parallel line at 0.002, and this is our yield strain, and this value is 0.002 plus 0.87 Fy upon E. Okay. So this is when the stress is equal to 0.87 times of Fy. So these values are different for Fe415 and Fe500. If you look at the actual curves, the values are 0.79 Fy for Fe415 and 0.75 Fy for Fe500. Okay, we don't have to bother about these values. This is just a build up to what the final equation is. We have established two things. One is that the failure criteria is epsilon c is equal to 0.002, and at this value of strain, the stress in concrete is 0.45 FCK, and the stress in steel depends upon what grade of steel it is. So if we go back to basics and try to find out how much is the compressive force that a particular section can resist at this strain, So the final axial load is equal to the stress in concrete times area of concrete plus the stress in steel times area of steel. So I can rewrite this as the stress in concrete times the gross area minus area of steel uh, plus the stress in steel times area of steel. I can rewrite this as the stress in concrete times the gross area plus the stress in steel minus stress in concrete times the area of steel. So I've just uh, shifted this term here. So Fs minus Fc into As. Now the question is, what is Fc and what is Fs? We have seen that for a strain value of 0.002, which is our failure criteria, our Fc is equal to 0.45 FCK. So I can rewrite this as 0.45 FCK into gross area plus whatever is the stress in steel, because the stress in steel depends on the grade of steel, minus 0.45 FCK. Please pardon my writing here. Just let me know if you do not understand anything. Times area of steel. So this is the equation that we have here. This is the simplest equation that you will get in this course. So this is 0.45 FCK Ag. Simple. Stress into area. Stress into area. That's what you've done everywhere. That's what we have started with. So we want force. So stress is equal to force upon area. Therefore, force is equal to stress into area. So this is stress into area for steel and concrete. So 0.45 FCK Ag plus now here I've used very raw notations. Here these are specific notations. FSC means the stress in steel and compression. So FSC minus 0.45 FCK into ASC. ASC means area of steel and compression. Now FSC has different values. Okay. So this is a design strength, or this is the magnitude of load that the column can take when it is under pure axial compression. But the code says that we must design column for a minimum moment also. So if this minimum eccentricity or this minimum moment is also to be taken into consideration, we'll have to design the column for this value of load plus a certain MUX and a certain MUY. Now, what the code does is the code simplifies this formula itself so that automatically the column is designed for a minimum value of moment. So the code says that though theoretically this is the formula, but you can use a simplified formula which is given here. This simplified formula is zero point 0.4 times of FCKAG plus 0.67 times of Fy minus 0.4 times of FCK into ASC. So what the code has done is simply reduce this value by approximately 10%. If you see, 0.4 is approximately 0.9 times of FC, 0.9 times of 0.45, or it is 90% of 0.45. So the code sort of reduces this value approximately 10%, and it gives a single value of the stress in steel irrespective of what the grade of steel is. So it has simplified this as well. So we do not have to remember three different equations, or we don't have to remember three different numbers. There is just one number that we have to remember, and then this 0.4 comes by reducing this by 10%. The final equation that we have is 0.4 FCK AG plus 0.67 FY minus 0.4 FCK into ASC. Simple. So this is the only equation that we are going to use in the design of columns. Okay. So with this, I think we have finished an introduction to the design of reinforced concrete columns under axial compression only. If you consider columns under uniaxial bending and biaxial bending, it's a different research, it's a different topic altogether. So we have just looked at very simple columns. that are expected to be under axial compression only. Okay, so any questions here? So how much percentage of this did you understand? Okay, I see that the meeting is on. My mic is on a mute, and I believe that you can hear me. So can you please answer this question as to how much percentage of this did you actually understand? So out of 58 people, is any one person awake?
We understood some of it. We'll have to go through again too.
Okay. So what we'll do is we'll just quickly start one circle, and we'll just try to convert this some understanding into reasonable understanding. Okay. So please write down, design a column. Design a column to carry an axial load of 2000 kilonewton of 2000 kilonewton. Draw a neat sketch. Draw a neat sketch to indicate the steel reinforcements. To indicate the steel reinforcements. Use M40 concrete and Fe 415 steel. Use M40 concrete and Fe 415 steel. Okay. So uh, some relief is that this is the easiest numerical that you will get in your examination. The shortest and the easiest. So what is being given is that the axial load is 2000 kilonewton. Uh, uh, please don't write this. This is something that I want to discuss first. So now, the question says that design a column to carry an axial load of 2000 kilonewton. The question does not say if this axial load is service or factored. If the question would say that the load is service load, design a column to carry a service axial load of 2000 kilonewton, it would mean that this is actually a service axial load, and to get the factored axial load or to get the ultimate axial load, we would multiply this by 1.5, and then the value that we would play with would be 3000 kilonewton. Don't write this, okay? But it is not mentioned in the question, so we're not sure if it is an actual value or it is factored value. So whenever we're not sure, we just start with an assumption. You can assume that this is a factored value. Just mention that this is your assumption, and then you can go on and solve the problem, or you can just assume that you can just say that assume that this is the service value. So the actual value is this. So the ultimate value is this, and then you can go with your solution. Now the easiest thing is that just assume that this is a factored value. The first step is assume that 2000 kilonewton is the factored action load. Please note that if the problem states that this is a service load, don't start with this assumption because there's nothing to assume, it is already given. And therefore, our PU is equal to 2000 kilonewton. Okay, I repeat that these are all suffixes. So PU is equal to 2000 kilonewton. And what else we have? We have FCK is 14 megapascals. And what we have is Fy is equal to 415 megapascals. And we have to design this column. So when we say the column is to be designed, what this means is we have to find out the dimensions of the column. We have to find out the amount of longitudinal reinforcement, amount of transverse reinforcement, and the detail. So there are four things here. The first thing is sizing of the column. Now, what do we know that can help us size this column? If we go back to our design slides, what is the information here that can help us size the column? The code says that the minimum reinforcement is 0.8, the maximum reinforcement is 6, but we stick to 4. So now we have a range in which we can provide reinforcement. That is 0.8% of AG to 0 to 4% of AG. So what we can do is we can start with an assumption that assume the percentage of longitudinal reinforcement to be something between 0.8 and 4%. Can you suggest a number? What seems like a good start? Any number between 0.8 and 4%.
2%.
Yeah, we can start with 2%. Okay. So it seems like a reasonable number, not too less, not too, it's not a very small amount of reinforcement, not a very high amount of reinforcement. So we can start with 2%. So now we are assuming the percentage of longitudinal reinforcement to be 2%. So what this means is ASC is 2% of AG. Again, please note that this is suffix. It is for the ease of writing that I'm just writing it normally. So ASC is 2% of AG. I can rewrite this as 2 by 100, which is 0.00, 0.02 times of AG. ASC is 0.02 times of AG. Now, what else do we know? We also know this equation that sort of helps us get a value of actual load. When we know FCK, we know AG, FY, and ASC. If we look at this equation, just a moment, I'll just take a screenshot of this. If you look at this equation, we know this value. That is the value for which it has to be designed. We know FCK. We do not know AG. We know FY, FCK. AC is something that we've just assumed, so we know AC. So if I use this equation, I can find the value of AG. So the design strength, I'm just writing the meaning of this equation. There's no confusion. Design strength in actual compression considering the effect of minimum eccentricities. So that is what that equation stands for, minimum eccentricities. And this equation is as per IS 456 2000. So we know that PU is equal to 0.4 times FCK times the gross area plus 0 point times the stress in steel minus 0.4 FCK times area of steel in compression. Now I just have to plug in all the numbers. So RPU is 2000. Now the the thing that we have to take care is the units on both the sides have to be consistent. FCK is in megapascals. Megapascal means Newton per mm square. AG we would use in mm square. So mm square gets cancelled. The term is in Newton. So this term is in Newton. Similarly, even this term is in Newton. Therefore, this has to be in Newton. So this 2000 is in kilonewton. To convert it in Newton, I'll multiply it by 1000. This is equal to 0.4 times FCK is 40 times the gross area. This is the area that we do not know yet. Plus FSC. Please make a small correction here. This FSC is actually 0.67 times Fy. So I just wrote FSC, but this FSC is actually 0.67 Fy. So 0.67 times Fy, which is 415, minus 0.4 times 40 again, times ASC. We have seen here that ASC is 0.02 times of AG. So I can write this as 0.02 times of the gross area. Now I just have to solve this equation to get the value of gross area. So I can write this as 2000 and then 3 more zeros is equal to, this is 16 times AG plus 0.67 times 4 and 5 minus 0.4 times 40, which is equal to 262.05 into 0.02 is 5.241 times of AG. So this is equal to 21.241 times AG. Therefore, AG is equal to 2, 1, 2, 3, 4, 5, 6 divided by 21.241. Can someone give me this number? So what I get is approximately 94157.5, whatever. I can approximate to 94158. What would be the unit of AG?
mm square.
Mm square. Good. So now I've got the area of column, but I don't know the dimensions yet. So what can I do to get the dimensions of the column? A simple thing that I can do is I can assume the column to be square, which means that the dimension square is equal to AG. Therefore, B is square root of AG. I'll just write it as SQRT times SQRT of AG, which is equal to square root of 94158, which is approximately 307 mm. So what would you choose the dimension to be? If approximately you are getting 307, what dimension will you provide? Come on, not a very difficult question. If you cannot provide 307, right? You cannot give in your drawing 307 by 307 column. You'll have to approximate it to say something in multiples of 25 or 50. So what dimension will you provide if it is 307? Sorry?
100 maybe 3.
Sorry, but I could not hear you. What will you provide B as? 300. Simple. Why should it take so much time to answer this? You could either approximate it to 300. Don't write this, okay? You can approximate it either to 300, or you can even say 325 or 350. It's okay. Now, what does it mean? So when you approximate 307 to 300, what it means is that the area of steel that you will actually get would be slightly, very slightly, okay, greater than 2% of AG. Why very slightly? Because 307 is very close to 300. So if you assume it to be 300, this is what will happen. If you assume it to be 325, your area of steel would be slightly lesser than 2% of AG. Do you understand this? Why does this happen? Can someone please answer if you understand why does this happen?
Can you explain this, please?
Okay. So the for a 2% reinforcement, the width that I require is 307. Practically, I cannot provide 307. I can provide either 300 or 325. Let me just get rid of this so that there's okay. So I can either provide say 300 or 325. If what I'm saying is if I provide 300 mm, the area of steel that I will get would be slightly greater than 2%. If I provide 325, the area of steel that I will actually get, this is an assumption, okay? We have to calculate the area of steel again because this is just an assumption. So if I provide the width as 325, the area of steel would be slightly less than 2%. So do you understand why this happens? Or what does this mean? Okay, this is not a technical question, it is simple logic. So 2% means 307. Okay. In any column, the contribution is from concrete and from steel. So for 2%, you require 307. Let me write it other way. For 307, we require 2% of steel. If I make it 300, which means that I'm reducing the contribution of concrete, meaning that the contribution from steel has to go up. So this would be slightly greater than 2%. If I approximate it as 325, meaning that now I have increased the contribution of concrete, meaning that the contribution of steel that would be required would be slightly less than 2%. Do you understand this?
Yes.
This is nobody going to ask you this. This is just that so that you understand what's going on. So I can approximate either 300 through to 325, doesn't matter what I approximate it to. It has to be close to 307. So now what I've got is I've got a size of the column. So let us let's just keep this in bracket. You don't have to actually do it in the examination. Let us just see what happens if we provide or let's do one thing. Let's forget this. Let's go with a normal procedure. So now we've got a size that we have got a 300 by 300 column. So with this, we have finished the sizing of the column. The next step is to, okay, before that, we just need to write a statement that uh, provide a 300 mm by 300 mm concrete column. Now the next step is the design of longitudinal reinforcement. Now let us go back to our equation. Okay, in this equation, when we knew everything except AG, we started with an assumption for ASC and then we found out AG. But now if you look at this equation, we know the exact amount of AG that we are going to provide. We know FCK, we know FY, and we know the actual value of load. We know the value of actual load for which the column has to be designed. The only thing that we do not know now is ASC. Do you understand the difference between step 1 and step 2?
Yeah.
In the first step, we assumed something for the ASC, then we calculated AG. Now this is the AG that we are going to provide. For this provide, so this is the true value. Okay. So I'll just repeat this one more time to ensure that there's no confusion. Okay, so this is, we have a true value for FCK, we have a true value for PU1, a true value for, so I'll just write this as T, 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 and T. What we do is we assume ASC and then we compute some AG. Then what we do is from that AG, we calculate what is the width of the column required. Then we look at the practicality and then we provide some AG. When we do so, our equation would change. So how will it change? So now what we have is we also have a true value of AG. So this is something that we had assumed before. Now we'll use the same equation to find the true value of ASC. Any questions? Okay. So design of longitude.
Yeah,
Yeah.
Bhargav.
Yeah.
Yeah, but we assume the value of AC as well, right? With like 2%. So even that's not like we have used that value in the calculation. So
Yes. 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 You're correct.
the
Yes. Go on.
so the value of AG that we have got, how do we know that it's a true value?
Could you please repeat your question?
We have assumed the value to be 2%, right? AG
Yes.
is 2% AG, and we have used that value in the numerical. So the
Yes.
value of AG which we have got now, how do we know that it's the true value?
Okay. So see, uh, design. Okay. Let me put it this way. So in analysis, when I say analysis, what I mean is when we try to find out this value, say 2000, when we try to find out what is the load for which something has to be designed. So that is called analysis. In beams, we have to find out moment, we have to find out shear. In this problem, we have to find out axial force. So analysis always has one correct answer, irrespective of what is the method that you use for analysis. But design, in which we sort of finalize the dimensions, we give reinforcement, there is no one correct answer to design. There are a million ways in which you can design. Okay. So if you ask, say, 5 different designers, if you give this problem to 5 different designers, you can expect 5 different solutions. But all those solutions could be correct. Meaning that we have started with the number, say 2%, because I'm comfortable in providing 2% of reinforcement. And then I've calculated the size that would be required for 2% reinforcement. In other ways, I have calculated area of steel and area of concrete uh, such that I can resist the load of 2000 kilonewton. I started with an assumption of 2% of area of steel, and then I calculated the corresponding area of concrete. Okay. Now let us say that I feel 2% is a bit too much. I don't want to spend that much on my reinforcement. Okay. So I say I'm going to start with 1% reinforcement. Okay. Before I explain further, would someone like to answer this question as to what will happen if I choose the value of ASC to be 1%? Will you get B less than 300 or greater than 300? Simple question. We started with an ASC of 2%. We got the width of concrete to be 300. If I say I start with ASC of 1%, what is the width that I will get? Will it be greater than 300 or will it be less than 300?
Greater.
Greater than 300, right? It's an obvious answer. Now, why is it so obvious? Time and again, I've been repeating that this 2000 that I have to resist, okay, is going to be because of concrete and because of steel. So if I increase the contribution of steel, the contribution of concrete can automatically reduce. If I reduce the contribution from steel, the contribution from concrete has to increase. So say for 2%, the value that I'm getting is 300. If I reduce the contribution, that is, if I reduce from 2 to 1%, this is going to be greater than 300 because the contribution from concrete has now to should now increase. And that is the reason it is obvious that if I shift from 2% to 1%, this 300 will go somewhere to say 400, 450. Okay. So now the question is, how do we know that 2% is correct? The thing is, there is no correct and incorrect here. It is always, it always depends upon how much reinforcement are you comfortable with and what dimension of the column are you comfortable with. Okay. Now, if I ask one of you, if first thing you ask me that, this is the span, and then I say that we need a column of 300 by 300, but we'll have to provide 2% of reinforcement. Now, from my experience with architects, all of you would say that, okay, 300 by 300 seems to be a reasonable dimension. It is not taking up a lot of my floor space. So fine, you go ahead and build a 300 by 300 column. Okay. I could have started with 1% of reinforcement here, and I could have, say, got 450 mm. I could come to you and say, I need 400 by 400 column, a 450 by 450 column. Now, a lot of you might have sort of argued that could we please provide lesser dimension for the column. I'm not comfortable with providing this much of area. I'm not comfortable with the floor area that I'm getting with 450 by 450. So there's no correct or incorrect here. It's always uh, the amount of reinforcement and the amount of concrete that you want. The reason why I start with 2% is normally, yes, the amount of steel that you would that should be reasonable in the column is 2 to 3%, and therefore there's always another number that you could start with. Could I answer your question?
Yeah.
Okay. So at least from your confidence, I get that I could answer your question, and I hope everybody else also understood. See, nobody is going to ask you in the examination as to what is the relation between the area of concrete and area of steel. What happens when you reduce this? What happens when it increases? The only intention is you understand practically what is happening. We can always just mechanically follow the procedure and get an answer. But if you do not understand what this answer means, what is the other way you could have done it, then I feel there's no point in me teaching you this. So if in say in your projects or in your actual practice, if structural engineer says that okay, this is the minimum size of the column that would be required, and you're not comfortable with, you can always ask the structural engineer to increase the amount of reinforcement in the column. Well, if it's practically possible, because there might be a case that he has started with an assumption of a lower percentage of reinforcement. Therefore, the right question to ask in that case would be, what is the percentage of reinforcement that you have assumed? Okay, and if I know it's a bit too ambitious, but if you happen to remember that I've taught you that it has to be between 0.8 to 4%, you could always argue that okay, 1% is too less. You would always go to 2.53% and just reduce the size of the column. Okay, so that is the right question to ask as an architect. So now we are going to design the longitudinal reinforcement. Now what we have is PU is equal to 0. I'm just writing the equation again. So PU is equal to what I have here is 2000 into 1000 is equal to 0.4 times 40 times gross area. Okay, the gross area is 300 by 300. So see, I've checked more than 100 papers, and a common mistake that I see is when it comes to gross area, students just write this number that we have got. This is not the right number. Okay, this is a gross area that you are actually providing. What you have provided is 300 by 300. So this is the gross area that you should use. Do not use the gross area that you've computed before. So this is 0.67 times 415 minus 0.4 times 40. The only thing that we do not know in this equation is area of seal and compression. Okay, so if I quickly solve this, minus 0.4 times 40 times 300 times 300. So what I get is 560000 is equal to 0.67 times 415 minus 0.4 times 40. 262.05 times of AC, which means that AC is 560000 divided by answer, which is 2137 mm square. So this is that amount of reinforcement that we actually require. Now, I just want you to do a small exercise just for your understanding. So this is not what you're expected to do in the exam. This is for your understanding. So let us try to compute what is 0.2% of Ag. 0.02 times our Ag is 300 by 300. So this is 1800 mm square. So let's just compare with what these numbers mean. Okay. So for 1800, what I required is 307. Okay. Let me write it the other way. For 307, we required 1800. So if I'm reducing 307, so if I say 300, we can expect this number to go up, and that number is 2137. So a common mistake again is everything is correct up to this step. What a lot of students do after this is that they just say, okay, AC is 2% of AG, which is 0.02 times of AG, and they calculate this value. So 1800 mm square. This is incorrect. This would be correct if you would provide a 307 by 307 column. So now this is the actual area that is to be provided. Okay. So now the question is, now we have area of reinforcement. Now how many bars to provide? So the bar sizes again, just for your understanding, the bar sizes, just for your information, the bar sizes that are available, one thing that we already know is the minimum has to be 12. So there's 12, then 16, then 20, then 25, then 32, and so on. So these are the bar sizes that are available in the market. So we can assume any of these sizes, we can assume any of the diameters, and then we can calculate how many bars are required. So looking at these numbers, I think using 20 could be an option. Therefore, say using 20 mm dia reinforcement, number of bars required would be equal to the number of bars required would be equal to ASC upon AB, that is the area of the total area that is required upon area of each bar. So this would be equal to ASC is 2137. Again, a common mistake, and this is actually really unexpected, that a lot of you even don't know the formula for finding out the area of a circle. So the correct the correct formula is pi by 4 diameter square or pi radius square. A lot of you do pi by 4 radius square, which gives you an incorrect formula, an incorrect value of AB, and thereby an incorrect number of bars. So this is equal to pi by 4 into diameter square. So this is pi by 4 into 20 square. Pi by 4 20 square is approximately 314. So with this, the number of rebars that we require is 6.8. So how many rebars will you provide if the calculation says 6.8? Anyone? Sorry?
7.
Okay, 7 could be an answer. Now I'll just draw a sketch and you could help me provide 7 rebars. So this is the 300 by 300 column that we are talking about. So 4 bars have to be in at the corner. So 1, 2, 3, 4. Where should I provide the remaining 3 bars?
Yeah, it have to be an even number.
Right? So if I provide 3, there's a void here. So I cannot actually provide 7. So the next possible number is 8. Okay. So when I say 6.8, I can approximate it to 8 bars. I can, which is approximately equal to 8 bars. So what I have finally, yeah,
Had it been
yeah.
less than 6.5, would you have given
No, if it would be any number more than 4, I'll have to provide 8 bars. Because let's say the number is 4.2. So in that case, I still require more than 4. I cannot provide 5 because this makes no sense. I cannot provide 6 because this makes no sense. One way you could do it is, you could provide bars like this. So 6 is still acceptable. So if anything is between 4 and 6, you could have provided 6 rebars. But if it is anything between 6 and 8, just a moment, I'll just write this again. So if there's anything between 4 and 6, you can provide 6. If there's anything between 6 and 8, you have to provide 8. And if there's anything between 0 and 4, you always have to provide 4. Okay, so we have approximated it to 8. Therefore, what we've done is provide 8. You can either write it as T20 or 20 and the diameter symbol. Longitudinal. Okay, just a minute. So our next step is over. That is, the longitudinal reinforcement is provided. The third step is lateral ties. This is pretty simple. There are just 2 criteria that we have to satisfy. A is that the tie diameter uh, it has to be greater than 6 mm. This is greater than equal to. So it has to be greater than equal to 6 mm. That's the first criteria. The second criteria is the diameter of longitudinal bar divided by 4. So it has to be 20 by 4, which is equal to 5 mm. So from this criteria, what is the diameter that you will choose?
6 mm.
6 mm, because it has to be greater than equal to. And therefore, we can say that provide six mm diameter. And the second criteria is the spacing. So for this, we have 3 criteria. This has to be less than equal to the first one is the least lateral dimension. Now, this is a square column. Therefore, both the dimensions are 300. Had this been a 400 by 300 column, the least standard dimension would be 300. So this is 300 mm. Then the next one is 16 times the diameter of longitudinal bar, which is 20. So this is equal to 320 mm. And the third criteria is an absolute number of 300 mm. Okay. So what will you provide?
300.
300 mm, because the tie spacing has to be minimum of these three. The minimum of these three is 300. Therefore, so finally what we have is provide 6 at 300 mm center to center. So with this, we have finished our problem of designing columns. Now the last thing that is left is the question says draw a neat sketch to indicate the steel reinforcement. So we'll just quickly draw a sketch. So it has to be a 300 by 300 column. Now we have to provide 8 rebars. So 4 at corners and then 1 at each of the sides. This is the longitudinal reinforcement. What we have to mention here is the dimensions. So this is 300. Because the final output has to be a drawing. So whatever we have done so far should be able to be communicated through this drawing. So this is a 300 by 300 column. Then we have to provide ties. So normally what is done in practice is whenever this spacing is greater than 75 mm, you want to remember this number, okay? This is for your information. Whenever this is greater than 75 mm, what is done is there's always a cross tie provided. And a similar cross tie is provided in the other direction. So one bend is a 90-degree bend and the other one is a 135 bend. This is a single loop. The outer one is a single loop. And here This is the 90-degree bend. This is the 135 bend. Okay, so what other information is remaining? First is about the reinforcement. So what we have provided is 8 bars of 20 diameter, and next information is that we have provided ties which are 6 diameter at 300 mm center to center. So we have to include all the ties, that is the outer tie as well as the cross tie. And one more thing that we have to mention is that what should be the clear cover. We can just write it here that the clear cover is equal to 40 mm. That is what is provided in the normal conditions. You could also just show it here. Instead of writing, you could just show that the clear cover is 40. And this completes our sketch. This is what should be shown in the actual drawings. Okay, so with this, we have completed the design of reinforced concrete columns. I really urge you to go through the presentation and this problem. And if you have any questions, any thoughts on?
Bhargav, I have a doubt.
Yeah.
This might be a stupid doubt, but so I know that we got the answer as 6.8 and we took it to be 8 for the ease of kind of putting it evenly throughout the column. But
Yes.
I mean, so is over reinforcing in columns completely different from how it is in beams? Like, is it okay to overestimate
Yes.
the? I just wanted to ask about that like relationship.
Yes. Actually, that's not a trivial question. That's a good question. So the concept of over reinforcement, or an over reinforced section, is that is a concept that we studied in beams, where then we say that if a beam is over reinforced, it might just have a brittle failure, and that is the reason we should never over reinforce. We should never have an over reinforced section in beams. Now, in beams, the failure could be a ductile failure or it could be a brittle failure. If it's an under reinforced beam, the failure would be ductile failure. If it's an over reinforced beam, the failure would be a brittle failure. In columns, normally the failure is brittle failure, because so there is, in beams, there's tension, compression, and in tension the reinforcement sort of yields, and there's a lot of deflection it can undergo. But under compression, there's going to be crushing of concrete, which is a brittle failure. Okay, and that is the reason why we are so conservative in designing columns, that we say that the maximum strain is 0.002. If we look at the stress strain curve for concrete, there is a lot of strain that can still take. So this is 0.002, this is 0.0035. Beam, we say that beam fails here. Column, we say that column fails here. The reason why we are being so conservative is that this failure is a brittle failure. Irrespective of how much reinforcement we put in, the concrete is going to crush. And that is the reason why we are not thinking about under reinforcing. We are not thinking about an under reinforced or an over reinforced section in columns because the failure is brittle by default.
Okay, okay. Thank you.
Yeah. Okay. So any more? Yeah, yeah. Go on.
I want to ask that for lateral ties, the number depends on the height, right? So, if I mean the length of the cord. So,
Yes.
if you're given, suppose that in the question, uh, if we're given the height and then like in the end, if we're asked to calculate the number of lateral ties, so do we just divide it or do we have to leave some like we'll have to leave some like some value on both sides, right?
What do you mean the unsupported height of the column?
Um, yeah, I mean that these lateral ties, like right now we know that they are at 300 spacing.
Yeah, yeah.
And then suppose if you're given the height of the column as 3 meters, so then
Yeah.
we say 10 ties or do we have to leave some count or like if there's a question?
No, irrespective of what is the height, if you're given spacing, if you're giving the spacing, then height is not of a concern. So, irrespective of what the height is, 3 meters, 4 meters, 2 meters, since you've already given the spacing, so you don't have to give, okay, 10 numbers. This is, okay, a simple answer is ties are normally given in terms of its diameter and spacing. It is not given in terms of the number of ties that are required over the height of the column.
Yeah, like I just want to ask that where does it start from? Like the tying of column. It can't
Where
be.
does it start? So, so uh, normally we started at 50 mm, 50 mm from the face of the beam. It actually depends. If you're designing it only for gravity, if you are designing it for earthquake in earthquake zones 2 or 3 or 4, like with increasing zone number, the intensity of the earthquake increases. So it depends if you are designing it for gravity only, or for earthquake zone 3 or 2 or earthquake zone 3 4. It depends on that. So but normally 50 mm should be a starter. 50 mm, 100 mm.
All right.
Yeah. Okay, so please go through the presentation and the numerical, and we'll have a test on the design of reinforced concrete columns on Saturday. I hope there's sufficient time. It's a very small topic, shouldn't take more than a couple of hours. So, before I forget, just mark your attendance.